Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help you out with number 4 in your Unit 3 homework. So let's see, it says a modern crossbow can fire a 400 grain arrow at 450 foot per second. And these are just numbers I kind of picked off of an average or, well, maybe somewhat high performance crossbow, but these are reasonable values. Let's see, the draw length is pretty short. In this particular case, we're going to use 15 inches. And what that means is that when you fire the bow, the string applies a force to that arrow over a distance of 15 inches. Now, this one was, given in some, kind of non-standard units, and that was deliberate here to give you a little bit of practice working with these units. First of all, let's convert these to more what I would call standard physics units, I guess. No doubt we're going to need the mass of the arrow. And this is given in grains. That's a unit of weight. So look up how many, let's see, maybe pounds per grain and convert this to pounds. Then look up how many kilograms per pound to convert to kilograms. Now, a pound and kilogram are two different things. There's not what I would call a really true conversion between them, but a kilogram of mass has a certain weight at the surface of the earth. You can use that like a conversion factor to figure out how many kilograms that arrow is. This thing right here, I'd go ahead and convert that to meter per second. This right here, convert that to meters. I'd probably start these problems by doing that. All right, now, part A, to find the time frame here. What you have to realize about this arrow is that it starts from rest. If I draw a picture and I call it picture 1, here's my arrow. It's not moving yet. You think about an instant before it's fired. Then what happens is the arrow gets accelerated up to the 450 feet per second. So what you want to do here is a velocity graph, velocity against time. And we're going to go ahead and use a constant acceleration assumption for this problem. Not really a good assumption, but it'll allow us to actually work this out. And at t equals 0, the arrow's not moving yet. Sometime later, which you don't know, the arrow is moving at some value, which is the 450 feet per second. Now, you can either put that number in feet per second or meter per second. It'll work fine either way. You just have to be consistent. Then you make your constant acceleration assumption. And remember, these have two types of equations you can write. One for distance, one for acceleration. I would go ahead and use the one for distance, the displacement, the delta x for the arrow. How does that relate to this graph? That's going to allow you to write an equation, and you should be able to get the time out of it. I got 0.0056 seconds when I worked it. All right, part B, use impulse momentum methods to find the average force applied to the arrow by the bow. So, remember how momentum works. The initial momentum of a system, I usually call it like mv initial, plus the impulse added to the system, F delta t, equals your new momentum, mv final. I write this down and kind of use it to guide me as I'm writing these. You're going to draw a picture now. Remember, impulse momentum diagrams. Hopefully you've watched my video on that. So here's maybe a picture of the arrow. Picture 1. Now 1 is before it's fired. So ask yourself, does it get a momentum vector? Then your second picture of the arrow is for the impulses. You're going to put an F delta t on. Ask yourself, what direction is the force applied by the string onto that arrow? And then our new picture, I'll call it picture 2 here. Another picture of the arrow, except now it's got a momentum. You can either put an mv2 or you can actually calculate a number. Take the mass times the velocity here. You might wonder, why isn't this picture 2? So this impulse is what's happening between the two states. Picture a snapshot in time. Any given system, it has a certain momentum. Then picture your digital camera going off a couple seconds later, showing a new mass and velocity and a new momentum. This is what's happening in between them, between the two photos. So usually if I label that picture anything, it's like, I might call this like 1, 2, and this is between 1 and 2, what's happening between 1 and 2. But anyway, once you get these pictures right, then the equation from it basically writes itself. And you should be able to find the average force exerted on that arrow. I got 637 newtons. Part C, let's see, use principles of work energy to find the force applied to the arrow. So write out the work energy theorem. PE1 plus KE1 plus work equals PE2 plus KE2. And ask yourself, position 1, here, before the arrow's fired, what would its kinetic energy be? Then you have to decide how to take this force right here into account. I would just use a work term. The work done on the arrow is the force, whatever force the string applies to the arrow, times some sort of distance. And that was given later in the problem, or at the end of the problem there. And then equals your KE2 term. So if you choose to use that force, use a work term to take that force into account, you don't need to worry about potential energies. They're just not relevant. And you should get the same number. You should get 637 newtons if I've done this all correctly. So anyway, hopefully this will get you through your homework here. Have a great day.